Today we're going to be taking a look at power functions. A power function, as I've written here, is f of x equals k times x to the power of a. Now here, k and a are both constant numbers, and a is the exponent of x. So k and a have to all be real numbers in order for this to be a power function. An example could include f of x equals, so the example would be f of x equals 2 times x to the power of 3. That's an example of a power function. So why do we need to study power functions? Because they look like normal functions right now, except for the fact they only have one term and they have a coefficient and an exponent. Well, we want to see their graphs. So different power functions have different graphs. So right now, essentially, if I have a graph, so firstly, we have f of x is equal to x to the power of 1. So 1 times x to the power of 1. This is a power function, right? It's the most basic power function you've learned, which is f of x equals to x. Or you can say y equals x. It has a constant coefficient and it has an exponent. Now another function would be y equals x squared, or y equals 1 times x squared. This is the constant coefficient and this is the exponent. Now as you can see, if we change the exponent, the shape of the graph completely changes. So what if I chose to put in y equals 1 times x to the power of 4? Well, this time the graph, yes, does changes, but doesn't change that much. So let's just put in a few more functions. Y equals 1 times x to the power of 8. Does that change? Not really, I guess. What about 6? So what about when the exponent is 6? So the black line, the black curve represents the graph of x to the power of 6. The red curve represents the graph of x to the power of 8. Now, one thing you can notice here is that all of these graphs intersect at, so all of these graphs, if you exclude the first graph, intersect at the origin, and also at -1, 1, and 1, 1. And then, if we zoom in a bit, so if we just zoom in a bit, after we meet above this point, after we meet above this line here, where y is equal to 1, if we continue to move up, as you can see, the trend of the graphs change. Below, when the graph has a lower exponent, a lower power, for example, x squared, so the graph with a lower exponent is actually, you can say, above the graphs of a higher exponent. After this line y equals 1, let me just type that down. After this blue line y equals 1 over here, we have the trend changing. We know that the graphs with higher exponents, are on top. For example, the red line is on top of all of the other graphs. Now this is for functions with an even parity. So what does that mean? That basically means, so having an even parity means, so even parity. So the parity of a function or anything means the evenness or oddness of this function. For example, so how do we decide the parity of a function? You look at the exponent. For example, these graphs all have an even parity because their exponents are even, 2, 4, 6, 8. They are obviously even numbers. So the parity of these functions are even. So let's look at, so we know that functions of an even parity generally have this curved shape. What about functions of an odd parity? Because that's probably a different situation again. So we look at functions with an odd parity, we compare them with functions with an even parity. So let's just look at this. So y equals 1 times x cubed. So as you can see, this new graph over here, has so if we compare these two graphs, y equals 1 times x squared and y equals 1 times x cubed, we see that the graphs are completely different from each other. So one thing we notice is that y equals 1 times x squared is symmetric from the y-axis, right? And this graph, y equals 1 times x cubed, is symmetric via the origin. Now, they of course still meet at 1 and 1 because, well, 1 to any power is still equal to 1, right? So obviously when you input 1 into any power function, the output would be 1. And they also still intersect at the origin, because 0 to any power is also still 0. But, so now the graphs change a lot, and this all depends on the parity of a function. For example, what if I typed in another odd parity function? For example, y equals 1 times x to the power of 5. Now, once again, the graph is this weird curve that starts from the top and goes down. But it's similar to the purple line, right? So odd parity functions also have the same shapes, or similar shapes. What about if we tried y equals 1 times x to the power of 7? This curve here would be still similar. This curve here would be still similar. And as you can see, the graphs also meet at 0, 0, and 1, and they have certain trends, which are really interesting. What about another line then? Y equals 1 times x to the power of 9. Now, this graph is even more similar to 1 times x to the power of 7. It's really, really close. So as you can see, functions with the same parity have really similar shapes. But I guess an exception, if you would call it, is y equals 1 times x to the power of 1, because this graph is darkly aligned, and it's not really similar to the curves. So now that we've explored a bit for what happens with odd and even parity functions and how their shapes are so different, let's look at what happens when we change the coefficient. Because before, all of our coefficients were 1. So what happens when we change it to 2, 3 over 2, negatives, irrational numbers, etc.? Well, let's try the even parity functions first. So let's try x squared. This is the original 1 times x squared function we have. It's a really normal parabola. What if I change this to 2? The parabola gets thinner. If I change it to 3, parabola gets even thinner. What if I change it to 100? Look at the parabola. It's really, really close to a tiny line. What if I change it to 1000? Or even if I add more zeros? This is completely a line now. We can't see a difference from this and a line. If someone gave you this graph, you'd probably think it's a line before you thought it was a parabola with a really high coefficient. So, as you can see, if you change the coefficient, the leading coefficient, or the only coefficient of a power function with an even parity, the parabola it produces gets thinner or closer towards the y-axis. Well, is this the same with negative numbers? Let's try -1. So first thing you notice is that the graph reflects over the x-axis. It literally flips over. So about -2, the graph gets thinner. What about -10? The graph is obviously thinner. And then we keep doing this, we have a line again. So basically, this is how it works for even parity functions. But does this work for all even parity functions, or does it only work for x squared? Well, let's try, let's say x to the power of 6. So firstly, y equals 1 to the x to the power of 6. We have this curve that, well, is a weird shape, but it's still a parabola. It's a parabolic shape. What if I change it to 2? What if I change it to 10? Well, now the difference is significant. The graph is significantly thinner again, and it's closer to the y-axis. What if I kept changing it? again, we'd finally get a straight line, which no one can differ from a parabola and a straight line. So what if I flip this? If I flip this, the whole thing will start again. The higher the smaller my coefficient gets. If it's negative, the closer the graph is to the y-axis. So if I change this back to -1, this is the original graph, flipped over, right? So that's for even parity functions. What about odd parity functions? For odd parity functions, let's just start out with y equals 1 times x cubed. This is our resulting graph. It's a weird curve, but okay. And then, what if I change this to 2? The graph seems to get a bit thinner, again, vertically. It gets closer to the y-axis. If I change it to 3, what if I change it to 10? The graph is significantly thinner. If I change it to a really high coefficient, now we have a line again, and no one can differ this from a power function and a line. So, essentially, what happens here is that as the coefficient gets higher, the graph sticks closer to the y-axis. Same thing as even parity functions. So what if I flip the graph over? Well, it reflects over the x-axis. Okay, great. So if I let the coefficient be higher, again, the graph becomes a straight line. So same thing for odd parity functions. What if I change the coefficient though? I'm sorry, the exponent though. What if it's x to the power of 11, let's say? For x to the power of 11, this is the graph. Again, it's a weird curve, but okay. If we keep changing this, if we keep increasing the coefficients, well, alas, get a straight line. So the properties are similar, except for when the exponent is higher, it takes a higher coefficient to let the function become a straight line on the y-axis. Meaning that if you increase the exponent, the graph will get wider. If you increase the coefficient, the graph will get thinner. So all depends on the coefficient.